The universe is a tapestry of secrets, woven with threads of light and darkness stretching billions of light years across. But hidden within its grand design, the cosmic web's delicate filaments are mysteries that defy even our boldest theories. These vast, invisible highways of matter and energy shape everything we see, yet they hold questions science still can't answer. From ghostly voids to unexplained cosmic signals, the filaments of the cosmic web whisper riddles that challenge our understanding of reality itself. Today, we're pulling back the curtain on 25 of these spine-tingling enigmas, phenomena so strange, they'll make you question what we really know about the fabric of the cosmos. Buckle up, this journey starts where the known universe ends. Deep in the veins of the cosmic web, scientists have stumbled upon a cosmic accounting error that just doesn't add up. The universe is missing matter, not the elusive dark matter we're always chasing, but the ordinary, everyday stuff that makes up stars, planets, and even us. According to our best calculations, roughly half the baryonic matter, the protons and neutrons that form the backbone of visible reality, should be threaded through the filaments of the cosmic web. But when we look, it's simply not there. Where did it go? Some suspect it's hiding in an invisible fog known as the warm-hot intergalactic medium, WIM for short. This faint, superheated gas is so diffuse, it barely interacts with light, making it nearly impossible to detect with traditional telescopes. Others suggest the missing matter could have been ejected into deep space by galactic winds or black hole outbursts, flung far beyond our observational reach. But here's the twist. If we can't find this lost matter, our entire model of cosmic structure starts to unravel. Galaxies are fed by these filaments, and without enough fuel, their formation and evolution don't match our predictions. It's like trying to solve a puzzle when half the pieces are deliberately hidden from view. Every time we think we're close, the universe reminds us it still holds its cards close to the chest. If the cosmic web is the skeleton of the universe, then dark matter is the unseen force holding it together. These colossal filaments shouldn't exist, not in their current sprawling, intricate forms, without something invisible binding them. Enter dark matter, the mysterious, gravity-wielding substance that outweighs ordinary matter 5 to 1. Simulations show that without it, the cosmic web would collapse into a formless haze, its delicate threads dissolving into chaos. Yet for all its importance, dark matter remains a cosmic ghost felt but never seen. Gravitational lensing offers our best clues. When light from distant galaxies warps around these filaments, it reveals the hand of dark matter at work, bending spacetime like an unseen sculptor. Some filaments appear far denser than visible matter alone can explain, as if an invisible scaffold reinforces them. But here's the puzzle: not all filaments behave the same. Some stretch thin and wispy, while others knot into dense superhighways of matter. Why? Even our most advanced simulations can't fully replicate the variety we observe. Theories abound. Maybe dark matter interacts with itself in ways we haven't detected, creating subtle ripples in filament structure. Or perhaps ordinary matter, like gas and stars, stirs the pot tugging at dark matter's gravitational grip. Every new observation deepens the mystery. The more we learn, the clearer it becomes. Dark matter doesn't just fill the cosmic web, it defines it, and until we crack its code, the universe's grand design will keep its most guarded secrets. Somewhere along the cosmic web's sprawling highways, physics seems to break its own rules. Astronomers have detected filaments blazing at millions of degrees temperatures so extreme they rival the cores of stars. These aren't just random hotspots. Entire threads of the universe's structure are glowing with unexpected fury, defying everything we thought we knew about these wispy tendrils of gas and dark matter. So what's superheating these cosmic wires? One leading suspect is chaos on a galactic scale. When galaxies collide within these filaments, the violence sends shockwaves rippling through the surrounding gas like invisible tsunamis of energy. Another culprit might be the monstrous black holes lurking in active galactic nuclei. As these behemoths devour matter, they belch out torrents of radiation and high-speed particles, essentially pressure washing nearby filaments with enough energy to turn them into celestial furnaces. Yet even these explanations fall short. Some filaments burn hotter than any known source should allow, as if there's an unseen engine embedded within the cosmic web itself. Current simulations can't fully recreate these extremes. When researchers plug in all the usual variables, the numbers still don't match the scorching reality out there. It's a glaring reminder that the universe operates on levels of violence and energy we're only beginning to grasp, and until we solve this thermal mystery, our map of the cosmos remains incomplete, missing the fiery signatures of forces we don't yet understand. Among the filaments of the cosmic web, where most structures burn with the heat of creation, astronomers found something utterly baffling, a place where the universe seems to have left the oven door open. Known as the Great Cold Spot, this cosmic chill stretches over 1.5 billion light-years, a region so cold it defies even the most well-established laws of cosmic microwave background radiation. It's not just a fluke or a gap in observations. This anomaly is real, persistent, and disturbingly out of place. The integrated Sachs-Wolf effect, which explains most temperature variations in the cosmic microwave background, can't account for this deep freeze. Normally, as light travels through the web's gravitational hills and valleys, it should gain or lose energy in predictable ways, yet this spot is far colder than any fluctuation should allow. So what's really going on? Some theorists point to an enormous void, a near-empty bubble in the cosmic web where matter is so sparse, it siphons energy from passing light like a cosmic heat sink. Others go further, suggesting this could be the fingerprint of something far stranger, a collision with another universe pressing against our own in some higher dimensional space. Then there's the wild card. What if the filaments themselves have hidden structures we can't see? Vast, tangled magnetic fields or exotic particles could be at play, bending the rules of physics in ways we haven't yet imagined. Even as simulations struggle to recreate this icy anomaly, one thing is clear: the Great Cold Spot isn't just a scientific curiosity. It's a glaring question mark written across the cosmos, daring us to rethink our understanding of space, time, and the very fabric of reality. The cosmic web's filaments aren't just rivers of gas and dark matter. They crackle with invisible energy. Stretching across unfathomable distances, these structures harbor magnetic fields far stronger than anything science predicted. We're not talking about faint whispers of magnetism here. These forces are powerful enough to sculpt galaxies, bending the paths of cosmic rays and even shaping the birth of stars. Yet their very existence throws a wrench into our understanding of how the universe weaves its tapestry. Where do these magnetic fields come from? Some theories suggest they're relics from the universe's infancy, frozen into the cosmic web during the Big Bang's turbulent aftermath. Others argue they're forged in the chaos of galaxy formation, spun up like colossal dynamos as gas swirls through the filaments at breakneck speeds. But here's the catch: neither explanation fully accounts for their staggering strength. If primordial fields seeded them, they shouldn't have survived billions of years of cosmic expansion unscathed. And if they're generated locally, the energy required defies what we observe in galactic collisions and star-forming regions. These magnetic behemoths might be more than cosmic decoration. They could be the unseen architects of galaxy clusters, channeling gas into dense knots where galaxies sprout like beads on a string. Charged particles trapped in their invisible grip might even explain some of the bizarre high-energy radiation we detect streaking through space. Yet for all their influence, these fields remain ghostly, detected only through their subtle fingerprints on light and cosmic rays. Until we unravel their origins, one thing is certain: the cosmic web isn't just a passive scaffold. It's alive with forces we're only beginning to measure. The cosmic web was supposed to follow a blueprint, a predictable pattern of thick and thin threads woven by gravity over billions of years. But scattered across the universe, astronomers keep finding filaments that defy the plan. These wispy strands, stretched almost to breaking point, are so tenuous they barely register in our detectors. According to supercomputer simulations, they shouldn't exist at all, or at least not in such ghostly, brittle forms. So why is reality disobeying the models? One possibility stares us in the face. We might be missing something fundamental about how gas behaves in these vast intergalactic corridors. The mathematics assumes a uniform flow, but what if turbulence or magnetic fields are at work, scattering matter into faint, nearly invisible tendrils? Then there's the humbling alternative: our technology could simply be failing us. These filaments emit almost no light, and their sparse gas doesn't absorb enough background radiation to leave clear fingerprints. It's like trying to spot a single strand of spider silk against the glare of a spotlight. Even our most advanced telescopes might be glossing over the finer details, tricking us into seeing gaps where none exist. But the implications run deeper. If these two thin filaments are real, they could rewrite the rules of cosmic infrastructure. Galaxies depend on these threads for fuel, like trees drawing water through roots. If the supply lines are thinner than we thought, entire models of galactic growth might need retooling. Every delicate strand we uncover forces us to ask, are we seeing the universe as it truly is, or just the fragments our tools allow us to perceive? The cosmic web holds its secrets tightly, and even its faintest threads might be hiding the most startling truths. The cosmic web wasn't built overnight, or so we thought. But when astronomers peered back into the universe's infancy, they found something that rewrote the timeline. Some filaments, those massive threads binding galaxies together, appear to have formed at breakneck speed, stitching themselves into existence far quicker than our models predicted. If the cosmic web were a city, these filaments would be skyscrapers that somehow sprang up before the foundations were even laid. So how could these vast structures assemble so fast? Our simulations suggest it should have taken billions of years for gravity to weave gas and dark matter into these colossal threads. Yet there they are in the early universe, fully formed, like cosmic highways built in a fraction of the time. One radical idea points to primordial black holes, tiny, ancient monsters born in the chaos of the Big Bang. These unseen relics could have acted as seeds, their immense gravity accelerating the clumping of matter into filaments far earlier than expected. Another theory flips the script on dark matter itself. What if it doesn't just sit there passively tugging on things? Some exotic forms might interact with itself, colliding, annihilating, or even emitting hidden forces, supercharging the growth of filaments like invisible construction crews working overtime. But here's the catch: if either of these theories is true, we're missing huge pieces of the puzzle. Primordial black holes remain hypothetical, and dark matter's secrets are locked away in experiments we haven't yet perfected. Meanwhile, telescopes keep spotting these precocious filaments, each one a silent challenge to our understanding of cosmic evolution. The early universe wasn't supposed to be this organized, yet the evidence is written across the sky, daring us to rethink how quickly the cosmos learned to weave its own web. The cosmic web is supposed to be a bustling network, threads brimming with galaxies, gas, and the invisible pull of dark matter, but some filaments tell a different story. These are the cosmic deserts, regions so eerily empty, they challenge our very understanding of how the universe assembles itself. Stretching millions of light years, these barren strands defy expectations. They should be packed with galaxies feeding on the gas flowing through them. Yet when we look, we find nothing. Are these filaments truly empty, or is the universe playing a trick on our instruments? One possibility is that they contain ultra-diffuse galaxies, ghostly structures so faint they vanish into the background glare of the cosmos. Imagine trying to spot a single candle on the surface of the moon. Our telescopes might simply be missing what's really there. Then there's the more unsettling option. What if the gas itself has been stripped away? Galactic winds from nearby clusters could have blown through like cosmic hurricanes, scouring these filaments clean. Or perhaps black holes, acting like invisible vacuum cleaners, have siphoned away the material needed for galaxies to form, but the implications run deeper. If these filaments are as empty as they seem, our models of galaxy evolution might need a rewrite. Galaxies are born from the fuel these threads supply. Take that away, and entire regions of the universe could remain permanently dark. It's a humbling reminder, even in the densest structures of the cosmos, absence can be just as puzzling as presence. Gravity may shape the cosmic web, but something else is giving it an unexpected twist, literally. Astronomers have spotted filaments spinning silently in the dark, rotating like colossal celestial ropes. This wasn't supposed to happen. These structures are so vast, stretching hundreds of millions of light years, that even slight rotation should require impossible amounts of energy. Yet there they are, slowly turning, as if the universe itself is winding up an invisible clockwork. What could set these cosmic threads in motion? One clue lies in the neighborhoods they pass through. When filaments brush against galaxy clusters, the gravitational tug of war might impart a subtle spin, like a slow-motion whirlpool forming where two rivers meet. Supercomputer simulations hint that these tidal forces could be enough to set the gas and dark matter wobbling, though the numbers still don't fully match the observations. Then there's the wilder possibility: dark matter itself might be stirring the pot. If dark matter isn't just a passive scaffold but swirls in hidden vortices, these currents could drag ordinary matter along for the ride. Picture a spoon swirling honey, only the spoon is invisible, and the honey is an entire filament of galaxies. Some theorists even speculate about exotic physics, primordial forces left over from the Big Bang that still ripple through the cosmic web, nudging it into motion. But the real puzzle is scale. A single rotating galaxy makes sense. It's compact, bound by clear forces, but a filament, these structures are so enormous, their ends effectively stretch beyond the horizon of the observable universe. For something that size to rotate in sync defies intuition. Yet the data keeps piling up. The cosmic web isn't static. It's alive with motion, a slow, silent dance we're only beginning to hear the music. And every new discovery spins the mystery deeper. Galaxy clusters are supposed to be connected by thick, luminous highways, filaments of gas and dark matter that should light up our telescopes like neon signs in the cosmic void. But when astronomers go searching, some of these expected threads just aren't there. It's not that they're hiding, it's as if entire stretches of the cosmic web's blueprint have been erased. So where did they go? One possibility is as simple as it is frustrating. We might be looking with the wrong tools. These filaments could be so faint, so thinly spread, that even our most sensitive instruments barely register them. Imagine trying to spot a single cloud in a moonless sky. Sometimes absence doesn't mean the thing isn't there, just that our eyes aren't sharp enough to see it. But another idea is more unsettling. What if our models got it wrong? The simulations predicting these filaments rely on assumptions: how gas behaves, how dark matter clumps, how gravity sculpts the universe over time. If any of those assumptions are off, the whole picture shifts. Maybe filaments between certain clusters are inherently wispier, their gas diluted by cosmic winds or scattered by ancient collisions we haven't accounted for. Then there's the tantalizing third option. Some filaments might not exist at all. Galaxy clusters can form tight knots without clear bridges between them, like islands in an ocean with no visible currents. If that's true, our understanding of cosmic connectivity needs a rewrite. Perhaps gravity works differently on these scales, or dark matter's pull isn't as uniform as we thought. Every missing filament forces a choice. Do we build better telescopes or rethink the rules? Until we know, the cosmic web remains a puzzle with pieces we can't quite place, a reminder that even the grandest structures in the universe still keep secrets. Scattered through the cosmic web's vast filaments, astronomers have stumbled upon an elemental mystery: pockets of gas brimming with heavy metals like iron and oxygen, far from any obvious source. These aren't just trace amounts. In some regions, the concentrations rival those found near bustling star factories or the remnants of exploded stars. Yet there they sit, suspended in the void, as if the universe casually sprinkled precious metals across its darkest highways. So how did these elements end up so far from home? One leading theory points to supernova, the violent deaths of massive stars launching their metallic ashes into deep space like cosmic shrapnel. Galactic winds propelled by the fury of newborn stars could then carry these heavy elements into the filaments, seeding them with unexpected riches. Imagine a forge scattering its sparks into the wind, only for them to land hundreds of thousands of light years away. But here's the puzzle. Some filaments contain more iron than even the most active galaxies should realistically produce. This has led to wilder ideas. Could ancient, hyperactive black holes have belched out metal-enriched jets in the universe's youth? Or might there be entirely undiscovered processes at work, like exotic particle decays or primordial chemistry left over from the Big Bang itself? The implications are profound. These filaments act as cosmic recycling centers, funneling heavy elements into new generations of stars and planets. If their chemistry is stranger than we thought, it could rewrite the recipe for how galaxies and even life-building materials are distributed across the cosmos. Every anomalous filament is a clue, a silent witness to forces we're only beginning to decode. And as we trace these elemental fingerprints, one thing becomes clear: the universe doesn't just build its web in darkness. It decorates it with the remnants of its own fiery history. In the grand design of the cosmos, everything has its limits, or so we thought. Yet scattered across the void are filaments that laugh in the face of cosmic constraints, stretching far longer than any model predicted. These are the two long filaments, threads of gas and dark matter spanning hundreds of millions of light years, defying the universe's own rulebook. If the cosmic web were a city, these would be bridges stretching from one continent to another, bending the laws of physics just by existing. How does the universe build something so vast without breaking its own rules? The principle of homogeneity, the idea that matter should be evenly distributed on the largest scales, demands balance. Yet these filaments stretch the definition of even, their sheer length challenging the very foundations of cosmology. One theory hinges on dark matter's hidden hand. Perhaps its gravitational pull is more intricate than we imagined, weaving these colossal threads like an invisible loom operating on scales we've barely begun to measure. Then there's the role of cosmic inflation, that explosive expansion in the universe's first moments. Could primordial ripples in spacetime have stretched these filaments like taffy, locking in their impossible lengths before the first stars even flickered to life? It's a tantalizing idea, but simulations struggle to replicate the extreme proportions we observe. The real puzzle lies in what these filaments imply about the universe's skeleton. If structures this vast can exist, our maps of cosmic evolution might be missing entire chapters, hidden forces or forgotten physics that shape the cosmos in ways we're only now glimpsing. Every time we think we've charted the limits of the cosmic web, the universe whispers back, "You haven't seen anything yet." The cosmic web isn't just smooth threads stretching endlessly through space. It's studded with strange, dense knots where matter clumps together in ways we never expected. These tangled regions pulse with gravitational energy, as if the universe itself tied tight, mysterious bows along its vast filaments. Some are so packed with galaxies and gas, they defy our understanding of how smoothly matter should distribute itself across the cosmos. What could forge these bizarre cosmic snarls? One clue lies in the echoes of the Big Bang. Primordial fluctuations, those tiny ripples in the infant universe's fabric, might have left behind pockets of slightly denser space. Over billions of years, gravity amplified these small differences, sculpting them into the knots we see today. It's like stretching a wrinkled sheet. The creases don't vanish, they grow more pronounced with time. Yet dark matter might hold the real key. These knots could mark places where dark matter halos, invisible gravitational anchors, cluster more tightly than usual. Like hidden whirlpools in a cosmic river, their pull might trap ordinary matter, forcing galaxies and gas to pile up unnaturally. Some simulations even suggest these halos host their own mini-filaments, weaving intricate subwebs within the larger structure. But there's a twist. A few knots are so dense they challenge our models entirely. Could unknown gravitational quirks be at work? Perhaps exotic physics left over from the universe's birth? Or might black holes lurking unseen be knotting the cosmic web like invisible fingers crimping a ribbon? Every tangled clump we find whispers the same unsettling truth. The universe doesn't play by orderly rules. Even in its grand design, it leaves messy fingerprints, invitations to look deeper and question what we think we know. At the edges of our cosmic maps, where telescopes strain to capture the faintest whispers of light, some filaments barely register as ghostly smudges against the darkness. These aren't just dim, they're nearly invisible, pushing the limits of detection even with humanity's most advanced instruments. If the cosmic web is a bustling metropolis, these filaments are its forgotten alleyways, so faint they almost vanish from the cosmic census. The mystery begins with their composition. Gas in these threads might be extraordinarily sparse, so thin, it's like trying to spot a single breath of air in a stadium. Without enough material to reflect or absorb light, these filaments become nearly transparent to our telescopes. Some could lack the critical density to ignite star formation, leaving them without the bright stellar beacons that make other filaments easier to spot. But there's a catch. Our technology might be painting an incomplete picture. Current observatories rely on specific wavelengths to trace these structures, like using a flashlight to search for fog. Only certain tools can reveal what's truly there. Gas in these filaments could emit light in ways we aren't yet equipped to measure, or it might be camouflaged against the glare of brighter cosmic objects. Then there's the radical possibility that our understanding of filaments themselves needs an update. Could these faint threads represent a different breed, structures born from quieter, less chaotic processes than their luminous counterparts? If so, their elusive nature wouldn't be a quirk of observation, but a fundamental feature of how the universe builds its hidden scaffolding. Peering into these half-seen strands isn't just about filling gaps in our maps. It's a test of whether we're truly seeing the cosmos as it is, or merely the fraction of it bright enough to catch our eye. Every faint filament we uncover forces us to ask, is the universe more subtle, more inventive than we've dared to imagine? In the vast cosmic web, galaxies aren't just drifting randomly, they're moving with eerie precision. Astronomers have discovered something startling. Along certain filaments, galaxies spin in unnaturally synchronized directions, as if choreographed by some unseen cosmic force. Picture a row of spinning tops, each twirling in perfect harmony, except these tops are entire galaxies, stretching across millions of light years. So what's behind this galactic synchronization? One leading explanation points to the filament itself. As gas and dark matter flow along these massive threads, their gravitational pull might nudge galaxies into alignment like leaves caught in a slow-moving river. This tidal torque effect could gradually steer their spins into harmony over billions of years, but there's a twist. Some alignments are too precise for gravity alone to explain. Enter large-scale cosmic flows, colossal rivers of matter streaming across the universe, remnants of its earliest moments. These flows might act like invisible currents, dragging galaxies into coordinated motion on scales we're only beginning to map. Imagine a gentle but relentless wind shaping the rotation of everything in its path. Yet even these theories don't fully account for the patterns we observe. Could there be primordial magnetic fields threaded through these filaments, subtly guiding galaxy spins like cosmic puppet strings? Or might dark matter, still an enigma, interact in ways we haven't yet imagined, leaving its fingerprint in the dance of galaxies. Every aligned galaxy deepens the mystery. These aren't just random celestial objects, they're clues to forces that shaped the universe long before the first stars flickered to life. And with each new discovery, we're reminded the cosmos doesn't just build its structures in silence, it moves them with a hidden rhythm, one we're only beginning to hear. Deep in the cosmic web, astronomers have uncovered filaments that shouldn't exist, not because they're too faint or too long, but because they're too young. These threads of gas and galaxies appear fresh, as if the universe wove them into existence long after the blueprint said construction should have ended. It's like finding a skyscraper in the middle of an ancient city with a construction date reading yesterday. Standard cosmology paints a clear picture. Filaments formed early, their structures set in motion by the gravitational tug of war between dark matter and gas in the universe's first billion years. Yet these youthful strands tell a different story. Their crisp edges and vibrant galaxy populations suggest they assembled relatively recently, long after their older siblings had already settled into place. Could our models be missing something? One possibility is that local chaos reshaped these filaments long after their birth. Galactic collisions or black hole outbursts might have torn ancient threads apart, only for gravity to reassemble them into new, deceptively young-looking structures. Picture a bridge collapsing in a storm, only for the rubble to naturally reform into a fresh span, nature's version of cosmic renovation. Then there's the more provocative idea: what if dark matter isn't as predictable as we thought? Certain exotic forms might clump faster or slower than standard theories allow, creating late-blooming filaments in pockets where its behavior diverges from the norm. It's like baking a cake where one corner rises unexpectedly, except here, the oven is the fabric of spacetime itself. The implications ripple outward. If filaments can form this late, our cosmic timeline might need adjusting. Galaxies could have access to fresh fuel supplies far later in the universe's life, rewriting expectations for how and when stars ignite. Every youthful filament forces a choice. Do we tweak our models or admit the cosmos still holds surprises in its construction manual? One thing's certain: the universe doesn't just build in epochs. It revises, rebuilds, and occasionally leaves us scrambling to catch up. The cosmic web isn't just a silent scaffold, it hums with eerie repetitions. Strange, rhythmic signals pulse along certain filaments, like echoes bouncing through the corridors of deep space. These aren't random blips, they're precise, repeating patterns, as if the universe itself is tapping out a message in celestial Morse code. One leading theory traces these echoes back to quasars, the brilliant, hyperactive cores of ancient galaxies. When these cosmic behemoths flickered out billions of years ago, their final outbursts might have sent shockwaves rippling through nearby filaments. Like a bell struck once but ringing for eons, these vibrations could still resonate today, subtly warping the gas and dark matter they pass through. But there's a twist. Some patterns don't match quasar activity at all. Instead, they hint at something more elusive: dark matter substructures. If dark matter isn't perfectly smooth but clumps into invisible halos within filaments, their gravitational pull could create rhythmic distortions in surrounding matter. Picture dropping pebbles into a pond at regular intervals. The ripples would form a predictable sequence. Only here, the pond is a filament, and the pebbles are knots of dark matter we can't even see. Then there's the wild card. Could these echoes be evidence of something even stranger: cosmic strings? Hypothetical defects in spacetime left over from the Big Bang. These ultra-dense threads might vibrate like guitar strings, sending gravitational shudders through nearby filaments. While purely theoretical, the idea tantalizes physicists, offering a potential window into the universe's first moments. Each repeating signal challenges our assumptions. Are we hearing the last gasps of long-dead quasars, the hidden dance of dark matter, or whispers from the birth of reality itself? The cosmic web doesn't just connect galaxies, it might be singing a song we're only beginning to decode. Amid the glowing tendrils of the cosmic web, some filaments refuse to play by the rules of light. These are the universe's quietest thread structures, so elusive, they cast gravitational shadows without emitting a single photon we can detect. No starlight, no radio waves, not even the faintest heat signature. Yet their pull is unmistakable, bending space-time like invisible hands tugging at the fabric of reality. What could these ghostly filaments be made of? Dark matter is the prime suspect, a substance that outmasses ordinary matter 5 to 1, yet interacts with light so weakly it might as well be a cosmic illusion. If these filaments are dark matter's purest expression, they'd explain why telescopes see nothing, while gravitational lensing reveals their heavy imprint. Picture standing beside an invisible river, unable to see the water but feeling its relentless current drag at your legs. But dark matter isn't the only contender. Some theorists point to primordial black holes, ancient relics forged in the Big Bang's chaos. These could lurk within filaments like beads on a string, their collective gravity warping their surroundings without a trace of light. Others propose even wilder ideas, exotic matter forms like ultra-dense quark nuggets or hypothetical dark atoms could be threading the cosmic web in ways our physics hasn't yet imagined. The challenge is hunting what we can't see. Astronomers piece together clues by studying how these filaments distort the light of galaxies behind them, like mapping a silhouette against a starry backdrop. Each observation tightens the noose around these phantoms, yet their true nature remains just out of reach. One thing's certain: if invisible filaments dominate the cosmic web, our visible universe might be little more than decoration, a glittering fringe on a tapestry woven from shadows. The cosmic web is often imagined as an unshakable skeleton, its filaments weaving the universe together across billions of years, but sometimes the threads snap. Astronomers have caught glimpses of filaments that appear to fray, split, or even vanish entirely, as if some unseen force took cosmic scissors to the fabric of space. These sudden disruptions aren't just glitches, they're cosmic mysteries begging for an explanation. One possible culprit lurks in the vast emptiness between structures. When filaments stretch too close to a cosmic void, an abyss of near-nothingness spanning hundreds of millions of light-years, their gas might get sucked into the void's gravitational drought. Picture a river flowing into a desert basin, evaporating before it reaches the other side. Without enough matter to hold the filament together, it could simply dissolve, leaving behind disconnected fragments like a bridge with its middle spans missing. Dark energy throws another twist into the puzzle. As the universe expands at an accelerating rate, this mysterious force might be stretching filaments to their breaking point. Over time, even the densest threads could thin out, their material spread so thin that the filament effectively vanishes from our detectors. It's like watching a taut rope slowly unravel, strand by strand, until nothing remains but faint, disjointed wisps. But before we blame the cosmos, there's a humbling possibility. Our instruments might be deceiving us. Some broken filaments could just be illusions, gaps in observational data where sparse gas eludes detection. Even the most advanced telescopes struggle to map these faint structures in their entirety, like trying to trace a spider's web by moonlight. A faint filament could appear interrupted simply because its dimmest sections slip below our radar. Yet the most tantalizing disruptions resist all these explanations. A few filaments seem to shatter asymmetrically, as if something tore through them. Could primordial black holes have plowed through like cosmic wrecking balls? Or does dark matter, usually the glue holding filaments together, sometimes clump in ways that destabilizes them instead? Every fractured thread forces us to confront how little we truly understand about the forces shaping the universe's grand design. One thing is certain: the cosmic web isn't static. It bends, it stretches, and sometimes without warning, it breaks, and each rupture is a reminder. even the mightiest structures in the universe aren't built to last forever. Some filaments in the cosmic web don't just linger in the darkness, they glow, not with the soft light of stars, but with fierce, unexplained radiation. X-rays, radio waves, and other high-energy emissions pulse from these luminous threads, as if the fabric of space itself has turned into a neon sign in the void. What could possibly power such brilliant displays? One answer might lie in chaos. When turbulent gas surges through these filaments at incredible speeds, particles collide violently, generating radiation like sparks from a grindstone. Superheated plasma, whipped into frenzy by galactic winds or black hole jets, could be lighting up these structures from within, but not all glows fit this explanation. Some filaments emit more X-rays than their visible gas content should produce, while others pulse with radio waves that don't match known astrophysical processes. Could there be invisible particle accelerators woven into these threads, cosmic versions of the Large Hadron Collider, revving electrons and protons to near light speeds? Magnetic fields, twisted like colossal springs along the filaments, might be launching these particles on wild rides, forcing them to shed energy as strange, jagged light. Then there's the truly enigmatic possibility, something entirely new. Certain emissions don't align with any known type of particle interaction, hinting at undiscovered physics at play. Exotic dark matter decays, primordial energy left over from the universe's birth, or even flaws in the fabric of space-time itself might be contributing to this radiant mystery. Each glowing filament is more than a cosmic curiosity, it's a beacon, drawing our attention to gaps in our understanding. Whether powered by chaos, hidden forces, or something beyond our current theories, one thing is certain: the universe doesn't just build its web in silence. Sometimes it sets it ablaze with light we're still learning to read. In the grand tapestry of the cosmos, some filaments refuse to follow the expected script. Stretching between galaxy clusters that shouldn't logically be linked, these bizarre bridges defy conventional maps of the cosmic web. It's as if the universe scribbled outside the lines, connecting dots no gravity-driven model predicted. Some span staggering distances, thin tendrils of gas and dark matter binding clusters that should be strangers to one another. Are these bridges cosmic coincidences, mere chance alignments of unrelated structures that only appear connected from our vantage point? Or could they be remnants of something far older, fragments of once mighty filaments that have since frayed, leaving behind these ghostly threads as their last whispers? Simulations suggest another possibility entirely. Vast, invisible rivers of matter, large-scale cosmic flows, might be funneling gas and galaxies along hidden currents, stitching together clusters across unimaginable distances. Picture an underground aquifer feeding distant oases, only here the water is dark matter and the desert is the void. Yet the most intriguing bridges resist all three explanations. Some exhibit densities and temperatures that don't match theoretical predictions for any known structure type. Could unknown gravitational anomalies be at play, warping the cosmic web into shapes we don't yet understand? Or might there be entire chapters missing from our playbook on how filaments form and dissolve over time? Every unexplained bridge forces astronomers to confront the same humbling truth. The universe doesn't just build its connections where we expect them. Sometimes it throws a thread across the void just to remind us we're still learning the rules of the loom. Among the cosmic web's bustling superhighways, some filaments stand out for what they don't do. No violent collisions, no bursts of newborn stars, just eerie, unfathomable quiet. These two quiet filaments drift through the universe like abandoned train track structures that should hum with activity but instead lie dormant, defying every expectation of how matter behaves in these dense cosmic rivers. So why the silence? One clue might lie in their temperature. For gas to collapse into stars, it needs to cool, shedding energy until gravity can pull it into dense knots. But some filaments appear trapped in a thermal limbo, too warm to condense, yet too cool to ignite the turbulence that typically stirs such structures. Magnetic fields could be the invisible hand here, acting like cosmic shock absorbers to dampen chaotic motions. Picture a pot of water kept just below boiling, never allowed to erupt into bubbles. Then there's the dark matter factor. If these filaments thread through regions where dark matter is unusually smooth, lacking the clumpy halos that normally kickstart galactic formation, their gas might simply have nothing to cling to. No gravitational anchor means no stars, no fireworks, just a slow, quiet drift through eternity. But the real puzzle, a few of these silent filaments sit amidst perfect conditions for chaos. Nearby galaxies rage with star birth and black holes spew radiation. Yet the filaments remain untouched, as if shielded by some unseen barrier. Could primordial forces be at work? Leftover physics from the universe's birth that keep certain threads locked in perpetual stillness. The implications ripple far beyond these quiet corridors. If filaments can suppress star formation entirely, entire generations of galaxies might be missing from the cosmos, ghosts never born, all because the universe forgot to turn up the volume in certain places. It's a reminder, even in the densest webs of matter, silence can be the most deafening mystery of all. Among the cosmic web's quiet currents, there are moments when serenity shatters without warning. Filaments, those patient, sprawling threads, can suddenly erupt with cataclysmic energy, as if the universe itself has snapped a taut string. These aren't gentle flares, they're titanic outbursts, blasting radiation and shockwaves across millions of light years. And what triggers them? The answers might rewrite our understanding of cosmic violence. Take active galactic nuclei, the monstrous engines at the hearts of galaxies. When these supermassive black holes feast, they don't just belch out light, they unleash torrents of high-speed particles. If a filament happens to be in the line of fire, that energy punches through like a lightning bolt through mist, superheating gas and igniting turbulence on an unimaginable scale. It's cosmic feedback at its most extreme, a black hole's tantrum echoing through the web's delicate structure. But some eruptions defy even this explanation. In a handful of cases, filaments have flared with no nearby black hole to blame. Could dark matter be the culprit? If particles of this mysterious substance occasionally collide and annihilate within filaments, their mutual destruction might release bursts of gamma rays or other high-energy signatures. Picture an invisible fuel scattered through the cosmic web that occasionally sparks, leaving behind only cryptic flashes as clues. Then there's the wildcard, cosmic strings. These hypothetical fractures in spacetime, if they exist, might vibrate like plucked wires, releasing violent waves of gravitational energy. A passing filament could absorb that shock, translating it into sudden, brilliant fury. No one's ever seen a cosmic string, but if these eruptions persist without conventional triggers, we might be glimpsing their handiwork. Whatever the cause, each outburst leaves a scar. Gas is stripped away, magnetic fields tangle into chaos, and galaxies along the filament's length might find themselves caught in a celestial storm they never saw coming. These eruptions remind us the cosmic web isn't just a static map. It's alive with forces that can explode into view, then vanish, leaving only questions in their wake. The cosmic web isn't just a static grid. Some of its filaments twist and contort like cosmic ribbons caught in an unseen wind. These warped strands bend at impossible angles, defying the gentle tug of gravity that should keep them relatively straight. It's as if invisible hands are kneading the universe's very fabric, leaving behind these perplexing curves for us to unravel. One explanation points to dark energy, the mysterious force accelerating the universe's expansion. As space stretches, filaments could be caught in the crossfire, dragged into unnatural shapes by the push and pull of competing forces. Picture a river current bending a strand of seaweed, except here, the current is the expansion of space itself, and the seaweed is a million light-year-long thread of galaxies. Yet some distortions appear too sharp for dark energy alone. Could higher dimensions, those theoretical realms beyond our 3D perception, be warping filaments from angles we can't even see? String theory suggests gravity might leak into these extra dimensions, subtly twisting cosmic structures in ways that look impossible from our limited vantage point. Then there's the humbler possibility: our measurements might be fooling us. Observing filaments from Earth is like trying to judge a sculpture's shape through fog perspective, and incomplete data could make straight lines seem bent. But when multiple telescopes agree on the same eerie curves, the anomalies grow harder to dismiss. Every warped filament is a riddle wrapped in spacetime itself. Whether shaped by dark energy, hidden dimensions, or something stranger still, they whisper a tantalizing truth: the universe doesn't just build its web, it bends it. And in those bends, we might find clues to forces beyond our current imagination. The cosmic web doesn't just stretch silently through the void, it hums. Not with sound, but with something far stranger, a faint universe-wide vibration, like a whisper woven into the fabric of reality itself. Scientists call it the cosmic hum, and it might be the closest thing we have to hearing the universe's hidden symphony. This hum isn't random noise. It's a rhythmic, persistent signal detected in the subtle warping of spacetime itself, as if the filaments of the cosmic web are vibrating like colossal piano strings. Some theories suggest it's the echo of quantum foam, the turbulent, frothy nature of spacetime at the smallest scales bubbling up into the macrocosm. Imagine the universe's tiniest fluctuations, amplified over billions of years until they resonate across the vast threads of the web. Then there's dark matter's potential role. If dark matter isn't entirely inert but shivers in collective motion, its oscillations could send ripples through the filaments, creating a gravitational hum detectable only through its ghostly influence on surrounding matter. It's like feeling the deep thrum of a distant drum through the floorboards, except the drum is the unseen bulk of the cosmos and the floorboards are space-time. But the most provocative idea: this hum could be proof of something even grander, primordial gravitational waves left over from the Big Bang, still reverberating through the cosmic web like an ancient bell struck once and never silenced. The filaments, acting as cosmic antennae, might be picking up these spacetime ripples, translating them into a hum that carries secrets from the universe's very first moments. For now, the origin of this hum remains one of cosmology's most tantalizing puzzles. Is it the murmur of quantum chaos, the song of dark matter, or the last echo of creation itself? Whatever the answer, the cosmic web isn't just a structure. It's a living, breathing entity humming a tune we're only beginning to hear. And in that quiet vibration, the universe might be telling us its deepest story. From invisible matter to glowing filaments, spinning threads to cosmic hums, we've journeyed through 25 of the universe's most bewildering enigmas, each one a crack in the foundation of what we think we know. These aren't just quirks of deep space, they're glaring signs that the cosmic web, the backbone of reality itself, holds secrets we've only begun to untangle. Every missing filament, every inexplicable signal, every warp and whisper forces us to confront a humbling truth. The universe is far stranger, far more inventive than our textbooks dared to suggest. But here's the thrilling part: each mystery is also an invitation. When filaments spin faster than physics allows or glow with unknown energy, they're not just defying explanation, they're pointing us toward new discoveries. The cosmic web isn't just a structure, it's a living puzzle, a dynamic arena where dark matter, black holes, and forces we haven't even named yet collide in ways we're racing to decipher. And every time we think we're close, the cosmos throws another curveball, reminding us that the greatest chapters of astronomy might still be unwritten. So what's next? The hunt continues. New telescopes peer deeper into the web's shadowy tendrils, simulations grow sharper, and with every breakthrough, the universe's blueprint gets a little clearer and a little weirder. Whether you're a casual stargazer or a die-hard space enthusiast, these mysteries belong to all of us. They're proof that the night sky isn't just a static painting. It's a story unfolding in real time, waiting for us to turn the page. If uncovering cosmic secrets fires up your curiosity, you're in the right place. Hit subscribe and let's keep exploring the unknown together, because the universe, it's just getting started.